Implicit differentiation, and that title, again, another one of those titles that when you first see it, you're like, I have no idea what that means. Yeah, exactly right. I sort of enjoy math titles like that. They're confusing to look at. But by the end of the lesson, you'll be like, okay, I know what implicit differentiation is. In fact, by the end of the first slide, maybe. Okay, so it starts with functions such as y equals 4x squared minus 7x plus 3 and y equals 2x plus 5 or x minus 10 cubed are in convenient form. I mean, you might think it doesn't look that convenient because that's like a quotient rule with a chain rule inside, but it is at least y equals. That's what explicit means when it's since one variable is expressed explicitly in terms of another variable. So first level of understanding explicit means full and clearly expressed, leaving nothing implied. That is, for our purposes, it'll say y equals, and we'll know what the function y is. And because that's all we've really done in high school, mostly, there's a couple of examples where we didn't do that. You might think, well, isn't everything explicit? And the answer is a big time no. Sometimes the equation is implicit. It's implied what y equals. We can figure out what y equals, but it doesn't say just y isolated equals. So that's what implicit is. Now we have seen at least one implicit one before when we looked at circles, x squared plus y squared equals 25. Do you see that if I gave you the x value, you could figure out the y value, but it doesn't say y equals. So that's the difference. This one is implicit, not explicit. And apparently that's what today's about, is how are we going to find the derivative of ones that are implicit? Now, if you're right with this, you're like, well, I could solve for y. Couldn't I just do that? Couldn't I just isolate y and then use what I've done before? And the answer is yes. Can we use those old methods? Yes. But it won't be convenient or always possible. There will be times when you won't be able to solve for y. You're like, give me a break. I can always solve for y. And I'll just write another one over here in a little thought bubble for you to think about. Y squared plus sine y equals x. To isolate y, I have no idea how you would do that because you've got to deal with a square root but also a sine inverse all at the same time. There's no good way to come up with that. And we don't try. What I'm going to teach you today means, yeah, as long as I got y's and x's, I can take the derivative. I'll be able to find the derivative. So don't worry about that. And you can stare at this if you want. You want to have some fun. Play with this and you'll find out that solving for y is no easy task. Well, if I move the sine y over, I'm already in trouble. If I do square root of this, it's not going to get rid of the squared, and it's certainly not going to get rid of the sine. So there's no order to do this. We've protected you from these all through high school to go, oh, until today we're like, we won't really do too much with these. We can still sub into this. This isn't that bad to sub into, but to actually solve for y is a monstrous problem and maybe even impossible. There are functions out there where it's been proven that it's impossible to get y by itself. Shockingly often. Yeah, it's bad news. It's bad news. You know, we've really treated you all the way through high school like everything's going to be a nice y equals equation, and that's just not the case when you get to real intense applications, especially engineering, physics, and the sciences. And that's why, all those of you who are going after first year sciences, that's why there's calculus there. Calculus is needed to even handle actually not that complicated an equation, really. It's just a y squared and a sine y and an x, but you're going to need some advanced techniques to be able to handle that situation. Well, after all that, I could tell the whole story of the first slide in one sentence. If it's not y equals, we're going to need a new method. And then I'm going to go play around for a while. So don't let this lesson freak you out as it's happening. Just follow along with each step along the way, and then it sort of comes together at the end. Okay. So the method of implicit differentiation allows us to easily, I believe that's true, easily differentiate relations such as the one above. It will be foreign. It will be weird when we first see it. So at first you'll be like, this isn't easy at all. But after a little practice, you'll find this method is pretty straightforward stuff. So, but we should do a quick review of the chain rule, just to make sure we've got the chain rule down pat. But I'm going to say things a little differently. You'll notice I speak differently in these examples. I'm using these to warm up on, and then I'll talk weird. I'll use some different words, or I'll say things in a different order. So don't be surprised by that. I'm setting the stage for later parts. So it says find dy dx, and we've found out that when we see dy dx in this chapter, we shouldn't just go, oh, take the derivative. We should be like, oh, take the derivative, and we're looking for x as the variable we're working with. So that dy dx tells you two things. Yes, it tells you take the derivative, but also x should be the independent variable that you see along the way. And I'm going to propose a new way to thinking about the derivative, which is we're taking the derivative of both sides. Like all the operations we've done before, it was always like, do this to both sides, like add 6 to both sides, square root both sides. And here it's going to be take the derivative of both sides. So I'm going to think of it this way. I'm going to go d by dx of y equals d by dx of 3x plus 7 to the fourth. Now that catches you off guard. That's okay. I'm going to do a lot of that in this lesson, is thinking of a derivative slightly differently of I'm going to do d by dx of both sides. Now the left side, interestingly, you've just wrote down dy dx. You have all the way along. You just said, oh, I'm finding dy dx. But remember you did that because that's a subtle little move there that actually is the whole key to the lesson. If we run into y and we're trying to take the derivative with respect to x, we just write dy dx. This side is a little more down our alley. Bring down the 4 and reduce the power by 1. And then chain rule, multiply by 3. So I'm going to collect that all up and then pause for questions about either the chain rule or the new way I'm writing these things. Or not writing. The writing's pretty much the same, but I'm saying words that are slightly different. Do you have any questions on that first one? I mean, you can be like, isn't this the same thing we were doing with chain rule? Yes. All I'm saying different is that I'm really taking the derivative of both sides when I do it. I'm doing it like an operation. All right. We'll do b here. Y equals f at x to the fourth. And at this moment, hopefully, you're thinking, we don't even know what f at x is. How are we going to take its derivative? To which I say, correctly, but weirdly to you, we didn't even know what y was over here, but we took its derivative. We wrote dy by dx. That was what we were trying to find out. So when we encounter things that aren't x's, we'll just write dy by dx, implying that's the derivative of whatever we're talking about. But I'm going to do it the same way I did the last time. I'm going to go d by dx of the left side equals d by dx of the right side. And that really brings derivatives into the operation fold. You could add something to both sides. You could subtract something from both sides. You could square both sides, or you could take the derivative of both sides. And that way of thinking helps to understand what happens over here is that I'm going d by dx of y, which isn't an x, so I can't just write 1 because I'm taking derivative of y with respect to x. And if that's new and weird, that's what this lesson is. This whole lesson might be wrapped up in that moment, is going, I don't know what the derivative of y is. So the best I can do is write dy dx. Okay, over here, a little chain rule. That f of x inside can be scaring you. That's okay. But all I'm going to do over here is bring down the 4 and reduce the power by 1. That part's not too bad. Then, chain rule says take derivative of the inside, but it's an unknown function. I don't know what this function is. And if this is really weird to you, that's good. That's exactly what we're working on today, is when you get to a function that you don't know, and you've got to take the derivative, you just write df by dx. And if your brain is freaking out right now, that's fine. That is totally fine. Notice it's exactly what I did over here. Please notice, it's exactly what I did over here. I brought the 4 down, reduced the power by 1. That's exactly what I did here. And then I took the derivative of the inside, which on this, in example A, was just 3. But over here, it's df by dx, because I don't know what function is in there. I don't know what that function is. Now the question blaring might be, how often does this stuff come up where you got to do this kind of thing? And unfortunately, the answer is often. Often the functions will either be unknown to us and we still want to take the derivative of them, or we don't know them yet, maybe. Let's try another one, because these are very difficult. Y equals f at x to the fifth. My new way of thinking is write d by dx on both sides. Think of it as an operator. I'm finding d by dx of y, and I'm finding d by dx of f at x to the fifth. When I encounter y, I don't know how to take the derivative of y because I don't know what y is. So the best I can do is write dy by dx. That is easily the most important sentence of the lesson. When you're doing derivative with respect to x and you encounter y, we really don't do anything. We just write, oh, that's the unknown in this question, dy by dx. This one, okay, derivative of f at x to the fifth would be df at x to the fifth over dx times, and that, again, I totally get if you're like, now it's just random symbols to me. It's all running together in my brain. But maybe this helps, times the derivative of the inside, which is 5x to the fourth. That's how this one's different than the previous one. I had to do the derivative of the outside, evaluated at the inside, times the derivative of the inside. And maybe that's the first time that weird way of me saying it starts to make sense a little bit, just a tiny bit. It's the derivative of the outside function. The outside function is f. So it's df by dx, but evaluated at the inside. The inside doesn't get touched yet. It just stays inside there. Then the derivative of the inside, which is the 5x to the fourth. That's tough. On purpose. Jumping right in with some tough ones to get the feel for what implicit differentiation is all about. It's about doing d by dx of both sides. And when you run into something you don't know the derivative of, you just write that, df by dx. Georgia. Oh, it'll boggle your mind, some of what's coming. I think about something like fluid mechanics and the incredible equations that come out of fluid mechanics, where it's all these different terms, and each of the terms represents something different about what's going on in the situation. So as situations become more complicated, there'll be more and more terms involved in what's happening. In the case of physics, lots of times we leave some of those terms out. So many physics people know. Sometimes we leave out friction because things get too complicated, or we leave out air resistance because things are too complicated. But as you go further and analyze those things, there'll be more and more of these extra terms that we want to talk about. Now, what you need to understand is then the next phase of doing a question like this was go, okay, here's what we do know about the function. And then we start talking about the function, and then maybe we can deal with the terms as we go. So it's weird because we're in the middle of the story here. We're developing algebraic skills to get ready for the crazy equations that are coming. Yeah? Great question. Oh, and I'm out of space here. I'll just scroll down to here. I think this one's quick though. Y equals f at x, but f at x has an exponent of 1/2 on it. So if I want to do d by dx, I do d by dx of both sides. And that's the really big moment of the lesson. These examples are just me playing around with the new method, which is writing d by dx on both sides. And if I encounter a function I don't know, then I just write that. I just go, oh, d by dx of y, I don't know what that is, so I write dy by dx, which actually is what we've been doing the whole time. We didn't talk about it too much, but we wanted to do derivatives. We wrote dy dx, which was the unknown in this question. In this one, bring down the 1/2 and reduce the power by 1. Then, so that's the chain rule. Derivative of the outer function. The outer function this time is square root, or exponent 1/2. Derivative of the outer function evaluated at the inner, so the inner stays in there. Then df by dx. And I'll tidy that up a little bit using the methods we have used. So this top will be df by dx, and the bottom will be 2 root f at x. Annoying and unsatisfying, I believe. The best lesson I can compare this part of the lesson to is collecting like terms in grade 9. You go 5x plus 9x equals 14x. You're like, That's pretty unsatisfying. I don't know what x is. I don't know what happens next. But it was all building. It was building towards tougher examples. But that's a mess of algebra. Even as I look at it, I'm like, whoa. I mean, as I was doing it, each step made sense to me, but by the time it's done, it's a real big disaster. So is there any specific steps you want to talk about that are weird to you? Georgia, thank you. What's that? Is it good? Oh, that's fun when that happens. When just saying it out loud helps to see what it was. Good. All right. Well, don't get too intimidated by this just yet. You'll just have to trust me. It's not as bad as it looks once you get going on it. And we got to get on to some other examples before we see where this is going. So let's rewind and go back to some easier ones, and then accelerate back into those tougher ones. These three examples here are the key ones of the lesson. If we can get through these three examples and have you go, okay, well, I get that. If we get that far, life's pretty good. Life's going to be really good in this lesson. D by dx, find d by dx of 4x squared minus 10x plus 9. Okay. This is really easy because here's why it's easy. To be able to understand B, we need to understand why A is easy. A is easy because we're finding d by dx and all the terms have x in them. When that happens, we're like, oh, that's last chapter. That's what we did last chapter. Everything we went to find the derivative of was using the variable in question. So here, derivative by dx of 4x squared is just 8x. Easy stuff. Derivative of negative 10x is just negative 10. And the derivative of 9 is 0. I'm going to write that just to really show what's going on here. When you're finding d by dx of terms that have x in them, derivatives are easy like they were last chapter. And I'll tidy that up with a very tiny step. So this one is to remind you when derivatives can be straightforward, is when you're going d by dx of something that has just x's in it. But when you encounter something that has y, we don't know what y is. So all we can write is, if we're finding d by dx of y, we just write dy by dx. And that is either unbelievably simple and boring, which is like, so Ms. Todd, you brought me in here today to tell me that when I see y and I'm doing d by dx, I just write dy by dx. I think I already knew that. I think that's what we were doing before we got here today. I'm like, yeah, but it needed to be defined specifically so that when crazy stuff happens, we're ready for it. So, big moment of the lesson right here. I'll put a big exclamation mark going. If you get what I just said there, you're in way better shape than you think. So let me just repeat it. If you run into a different variable than x, and you're going d by dx, you just write dy by dx. You're like, I don't know what this is. It's dy by dx. It's the derivative of y with respect to x. Okay? And in these questions, it's often what we're going to be solving for. So the fact that it's dy by dx is fine because that's what we're going to be solving for anyways. That's the unknown in the question. Okay, if you're good there, then we've got a chance at this one. D by dx of y squared, I'm going to write it slightly different. I'm not going to do anything in this step here. I'm going to write this as y squared, which hopefully moving forward you don't have to do when you see these, but I'll do it this time so you get the feel for it. When I see d by dx of y squared, I notice that I'm taking derivative with respect to x, and this is y. So I've got to chain rule this thing. Georgia. Oh, she's going to take a shot at the answer. Oh, this is exciting. Tell me, what is it? I think so. I'm just going to write it in a different order, and you tell me if I write the same thing as you, because I'm going to think of it slightly different, I think. When you tell me if it's the same as what you got. When I go to take the derivative of y squared, it's 2y. Bring down the 2, reduce the exponent by 1. But then I have to go derivative of the inside, because it's a chain rule. This is y squared. So now I'm going, now derivative of the inside. The derivative of y with respect to x is just dy by dx. Is that what you wrote, or did you have another square there? Yeah, right. Okay. I thought so. I thought when you said it, I was like, it's so good. It's so close. Yes, derivative of y squared is 2y. Absolutely, it is. But then, if it's not with respect to x, you got to go inside and take the derivative. To which I think some minds then will go, wait a minute. We never did that before. When we had d by dx of x squared, we never had to chain rule it. We just took the derivative of x squared and wrote 2x. To which I say, yeah, I know. We really should have chain ruled it. We really should have. D by dx of x squared is 2x. Now derivative of the inside, but what's the derivative of the inside? What's the derivative of x when we're taking derivative with respect to x? It's just 1. So we should have been chain ruling all the way along, but we didn't have to. So when we were learning basic derivatives, we sort of ignored that and left it on the shelf. So I say now, anytime there's an exponent, we should be chain ruling the inside. The good news is, if that variable inside is what we're taking the derivative with respect to, it won't affect the answer. We can still do derivative of x squared and still write 2x. We can still do that. But this is just, now we're understanding it a little deeper about what's going on. You're taking the derivative of x squared, which is 2x, but the derivative of the inside is just 1. That's what makes taking d by dx of x squared so simple. Simple. It wasn't simple. We kept our feet on the ground there a little bit when we were doing those derivatives, because the derivative of x with respect to x was just 1. This takes some getting used to, by the way. If on a scale of 1 to 100 you're like a 27 going, I kind of follow what you're saying, but I don't think I'm anywhere close to doing it myself, then we're in great shape. 27 is a great number at this point in the lesson. So don't get intimidated by this, because most people, once they get the gist of this, don't think this is one of the hardest lessons ever. Having said that, do you have any questions about C or D? All I did with D was do an old question the new way and see it's okay that we didn't have a method there. We didn't have to chain rule those. Well, let's try another one. D by dx of 3y to the 4th. First step is just to take the derivative the way we always did. And think of 3y to the 4th and just look at it. Bring the 4 down and reduce the power by 1. 12y cubed. But because it was y, there's a penalty to pay when you are taking derivatives with respect to x of something with y in it, is now I have to go to the inside. I'm going to put little tiny brackets around the y saying, really, that y now I got to go inside the power of 4 and go after the derivative of y, and so that's dy by dx. Maybe your brain's making a little click now. It goes, okay, so if the variable is not what I'm taking with respect to the derivative, all I got to do is take the derivative like normal, 12y cubed, then multiply by dy by dx, and that is completely right. It's really just chain rule. I'm chain ruling this thing, and I have to take the derivative of the inside as I go along there. We'll try one more, and then we'll pause for questions, because this one is the one I think most people make the jump. Once they see this one, they're like, oh, I'm starting to get the gist of what I have to do here. I get past 50 on the understanding level. One of my first year profs said, if you leave a lesson in university understanding it more than 50%, you've had a great day. Now you can go do the homework. That was his take on it all. Okay, d by dx. Is the first term difficult? No. It's x's, so d by dx of x cubed is just 3x squared. See this method, this new way of thinking of the derivative as an operation, when it runs into x's, there's no problem to be had. Next one, d by dx of 4x squared. That's just 8x. No problem so far. If we use the new method to do those and go and find the derivative of the inside of both of these is 1, so that's not a problem. Who feels good about this? Who can look at y cubed and maybe take a shot at it? 3y squared, absolutely. The new way of doing this, when you see a y, you go, yeah, I just still take the derivative, bring down the 3, reduce the power by 1. That's derivative of the outer function. Then what? Then dy dx. So hopefully that was 25 minutes of me talking for you to go, Oh, okay. So all I do is when I run into x's, I take the derivative like normal. When I run into y's, I take the derivative like normal, but then the derivative of the inside will be dy dx. That's the unknown in the question. And this is weird looking, I get it, an unsatisfying line of mathematics, because it's like, well, now what do I do? Like, well, I know, we're on our way. When we get to our final examples, on yours it says more examples, you'll see how we use it, okay? Anyone feeling confident? George is feeling confident, go ahead. Negative 4y dy by dx, and that dy dx is just chain rule. You take the derivative of negative 2y squared, which is negative 4y, and then you go derivative of the inside, which is dy dx. You don't like it? Okay, that's okay. You can not like it. Yeah, that's a nice thing about some math things. They really don't care if you don't like them. They don't get upset. They don't get offended. They're like, oh, that's fine. You can not like me. That's okay. Just to help, though, I said it a couple times, but maybe someone could use some different words. Why, when I did derivative of, say, x cubed and did 3x squared, why didn't I have to take the derivative of the inside? Now I'm starting to imply you should be taking the derivative of the inside every time. Why did you not have to? Yeah, it's already in terms of x. So when I took the derivative of the inside, I would have got 1. So if it makes you feel better, you can write little 1s here so that you're doing it the same way every time. But hopefully it won't take long before you're like, okay, I don't need to do that. So those little 1s are there. I won't write anything else there. Do you have questions? Okay, well, back to circles, I think. The following example illustrates the method of implicit differentiation. We differentiate both sides of the equation and solve for the resulting dy dx. Okay, that's explaining what's about to happen. Let me just do it. It says find dy dx. So when you get a situation like this, don't solve for y. Don't go manipulate around and solve for y. With our new method, we can just go, okay, d by dx of this side plus, not plus, equals. Done already? It's good, okay. Equals d by dx of this side. And do each term one at a time. So d by dx of x squared, why is that one easy? Because it's in terms of x. So d by dx of x squared is 2x. Good so far. Then d by dx of y squared, 2y, but then dy by dx. And then d by dx of 25 is still 0. Welcome back, everyone. How was it? It's good. Yeah. You've missed some important stuff, but I'll try and, as I continue the lesson, I'll try and backwards explain every example, over-explaining it for the people that were here, and they'll be nodding and answering. And when they're nodding and answering, I hope that makes you feel like, okay, well, as weird as this seems, what he's doing, apparently it's not that bad, because the people who are here are like rhyming the answers off, no problem. Okay, but I'll try and backwards explain as I go to try and incorporate everybody. Okay, so once I get to that line, it said find dy dx. Now I do isolate for this dy dx. So as it was happening, you were worried about the dy dx. You're like, yeah, but what am I going to do with it? In an actual example, you're just going to isolate for it. What we wanted was dy dx.
Attention teachers, the award ceremony rehearsal is over. Students are on their way back to class now.
Think?
The award ceremony rehearsal is over and students are on their way back to class.
So this stage of the question, whether you're understanding how we got there or not, is just find dy dx. That's what the final result was, find dy dx. I've got an equation that has dy dx's in it, and so I'm just isolating dy dx. I brought 2x over, and it became subtract 2x. I divided by the 2y, and I can tidy that up a little bit. dy by dx equals negative x over y. But this is a new feature of derivatives, that the answer will have x's and y's in it. And that is okay. Yeah, it will be okay that there's x's and y's in there, because if they give me an x, I can sub it in, and if I need the y, I can go back to the original equation and find out what y is. So that's okay. So I'll just put a check there going, yep, it's okay. I understand completely that with the x's and y's in there, you're like, oh no, what do I do? Like, it's not a problem. It is the smallest problem of the whole chapter, worrying about an equation that has x's and y's, because we'll have the x and the y when the question starts. All right, so that actually closes the circle. It was a circle? Okay, it closes the loop of this lesson that we started with this, going, how are we going to take derivatives of x squared plus y squared equals 25? And now I'm talking to the people who missed that part of the lesson. How are we going to find these derivatives when it's not y equals? And this is the method. We take d by dx of both sides. Some of it is easy and some of it is hard, but I'm going to do some extra examples coming up so you can see it all in action as well. Am I remembering this right? It now goes 1, 2, 3, 4. Is that right? There's 4 remaining examples. Okay, so big challenge on me. I'm going to try and teach both groups at the same time. The groups who were here for the first part of the lesson and the groups that weren't, because this looks scary no matter what group you were in. 2x to the 5th plus x to the 4th y plus y 5th equals 36. Now this says find the equation of the tangent. Now let me just underline that and remind you what we do when we see equation of the tangent. We've done enough of these that hopefully the steps, you remember the steps. So I'm going to write them out here explicitly so that we're clear on what the steps are, so that we know what we're doing in this question. Because in a new situation, we might be suddenly confused about what happens. Step 1 was find dy dx at the point given. This gives m tangent. That's how we found the slope. We first found dy dx. So in this question, I'm going to try and find dy dx, and I'll get to that in a second because this looks intimidating. And those of you who are here for the lesson maybe are less intimidated. You're like, I think we're okay. And I'll try and reteach that in a second. 2, sub into y equals mx minus p plus q, or y equals mx plus b, depending on who you are. So I know it's about split 50-50. When I gave a test, I gave that last test, some of you were using this and some of you using that. And that's fine, whichever way you want. I'll try and remember to do it both ways here. You're like, okay, that's fine. I remember how to find equation of tangents. What I'm worried about is this giant mess of an equation that you've got here, Mr. Todd, and how we're going to find dy dx. Well, it says find dy dx, so my move is to go, well, then I'm going to take the derivative with respect to x of each side. People who missed this part of the lesson. It's a new way of thinking about what d by dx is. It's a operator. It's like multiplying both sides by something, or dividing both sides by something, or subtracting both sides by something. I'm doing d by dx of both sides. And now I've got a list of derivatives to take. 1, 2, 3, 4 different derivatives, all with different levels of difficulty. If you're finding d by dx of 2x to the 5th, life is easy. The reason it's easy is because that term is in terms of x. It's just x's, and I'm finding d by dx. So I'm just going to take that derivative and stop there to try and incorporate people who missed this part of the lesson and go, well, some of it's still the same. When you find derivative of terms that are just x's, you just write the derivative, 10x to the 4th. Then I'm going to skip this one for the sake of the people who have missed that part of the lesson, and jump to y to the 5th and maybe get some help. So I got to leave a space here. I know what's got to happen here, so I know how much space I got to leave here. Just leave a bunch of space there and go after y to the 5th. This is what I'm after here, y to the 5th. So somebody who was here for that part of the lesson, tell me the derivative, and then we'll try and explain it to the people who missed this part. What's the derivative with respect to x of y to the 5th? Somebody's going to help me, and I want them to say it in 2 parts. Do you know what I mean by saying it in 2 parts, Georgia? She does. She's nodding. Good news. This can't be that bad. In 20 minutes, I've got them so they know what the 2 parts means. What's the first part, Georgia? Okay, hold on. Let me just repeat what she said, and she might have said it perfectly. She said, I'm taking the derivative of y 5th, and she says it's chain rule. Her brain is thinking of y to the 5th as having a little bracket around it. Bring down the 5, reduce the power by 1, and it's 5y to the 4th. That's exactly right. Life is so good. And then what's the next part? Yeah. It's good. When you encounter y and you're taking derivative with respect to x, we wrote dy dx. We've always been doing that. When we took derivative of y, we wrote dy dx. Oh, that's the derivative. What she's saying is when you run into y to the fifth and you're taking the derivative with respect to x, yes, first you do chain rule. You bring down 5, you reduce the exponent by 1, and you get 5y to the fourth. But then you got to take the derivative of the inside, which is the unknown in this question. It's the thing we're trying to find out. It's dy by dx. Okay, Georgia, since you answered that question, why didn't I have to take the derivative here in 10x to the fourth? Yeah, that's going to take some, that one's going to take some work, yeah. Yes? Yeah, the derivative of the inside was 1. So that's why we never had to do chain rule before on these, is because the derivative of the inside was always 1. So I didn't teach it that way. I didn't have to complicate it. But looking back now and seeing it from a bigger picture, we really should have been doing derivative of the inside. But not that you should start doing it that way. You shouldn't start doing it that way. But just know that it's no problem. Derivative of the inside is 1 here, so it's okay. All right. Well, now, I thought I saw a hand. Did I see a hand? No? Which one do you want, Ian? Ian wants this one? Oh, yeah, no. Then I'll get somebody who wasn't here for this part of the lesson to do this one over here, just to help you along a little bit. Well, what's derivative by dx of 36? 0. So that's still 0. So that's pressure's off there. Okay. This will be interesting. 2 terms here to deal with. Yeah? Ian wants a shot. Okay. Tell me, what do you like for the first term?
Well, it's
okay. Yeah, no, let's stop there. That's beautiful. He said the important first sentence is going, this looks difficult, but it's a product rule. I got to take the derivative of the first times the second, and I'll squiggle the first there. That's my first. Okay, so go ahead. I'm not taking the derivative with y. So the fact that the y is there doesn't affect my first term at all. I don't really care about that. Product rule is derivative of the first, which is 4x cubed, times the second, which is y. And if you're having trouble with this because you missed the first part of the lesson, this is the moment we might bring you closer to where we're at in the lesson. Now, derivative of the second, do you hear how he said just? Which is just dy dx. That's the big moment of the lesson. If I can get that part of it through to you, the rest of this is just algebraic details. When you run into y, and you're taking the derivative with respect to x, you just write dy dx. That's what we've been doing the whole time. When we did a very simple one, let me write it up here. Let's say we did y equals x squared. Then we'd write dy dx equals 2x. You didn't think anything of it, but what you were really doing was going, hey, if I take the derivative of the left side, I don't know what that is, so I just write dy dx. That's the unknown in the question, and that's what's happening here. Okay, I got us distracted. Is it going to be okay? Then times the first. So this is derivative of the first times the second plus derivative of the second times the first. And we've got a big mess here, which I'm going to just rewrite out here and just tidy it up a little bit. And again, if you weren't here for it and you just like 1% get that, that's totally fine actually, because all the examples now basically do the same thing. So I'm going to re-explain that a bunch of times. But this is a major league problem with a simple solution. We wanted dy by dx. That was what I was trying to come up with, was dy by dx. And dy by dx is buried deep in this meth twice. And it's difficult to see what to do to be able to isolate the dy dx. Ethan, question or answer?
Are you able to just factor it?
Yes.
Dy by dx, and then you move all the other terms over the other.
Yeah. Good news. If you missed part of this lesson, the only thing you really got to worry about is where is this dy dx popping in? Once I get that down pat, the rest of it is algebra that maybe we've seen before. Ethan says just move all the stuff that doesn't have dy dx over to the other side. So that's negative 10x to the fourth minus 4x cubed y. Those terms didn't have dy dx, so I'm going to move them over. And then, what did you say to do next?
Then you can factor out the dy dx.
Factor out the dy dx.
Whatever's inside the brackets, you divide that by the other side.
Yeah. And those of you, it could be right at that moment you're shaking your head a little bit going, oh, it's that common factoring again. No wonder you were such a weirdo about that last year in advanced functions. You know, like that common factoring just keeps coming back in all sorts of different situations. And then to get dy dx by itself, I get negative 10x to the fourth minus 4x cubed y all over x to the fourth plus 5y to the fourth. Oh, that's good, powerful mathematics. I'll say it out loud. I believe this is the most powerful mathematics I've showed you so far. That is great stuff. Yeah, it's good. It's great stuff. Question is not over, but we've got it on the ropes now. We're now winning here. And again, if you missed the part about the dy dx, don't panic about that. We'll fill that gap in with the other examples. So what's now? See, now, normally we'd go sub in x equals whatever. Right? So you're going, well, this has all x's and y's. And to which I go, yeah, it's okay, look. They gave me a point with x's and y's. So it's a little tougher subbing, but it really is the same game we've been playing. So sub in 1, 2. dy by dx will be negative 10 times 1 to the fourth minus 4 times 1 cubed times 2 all over 1 to the fourth plus 5, 2 to the fourth. Let's just make sure I plug that in right. I feel a little distracted all of a sudden. 1 cubed, 2, 1, 4, 5, 2, 4. Yeah, that's right. Can I do this line all in one step in my head? That's a negative 10. That's a minus 8. And this is 1 plus 80 is 81. Is anyone on the case in their calculator? Just to check if Mr. Todd's getting old here. Okay, now I'm going to do that fun trick that all you iPad people can do, right? When you run out of space in a page, just grab it all, make it a little smaller. And now I've got some extra space. I said 81. 2, 4, 8, 16 times 5 is 80 plus 1 is 81. Is it right? Oh, whew, still got it. And this reduces nicely. Negative 2 over 9 is what my brain tells me. And I'm just going to write what that means. That's the tangent. And so then y equals, so my equation of tangent is y equals negative 2 over 9, x minus 1 plus 2. Slowly trying to convince the y equals mx plus b people that maybe this is a little faster. It's just having this equation. If I was doing y equals mx plus b, I would get, even if you are a y equals mx plus b person, this might be a faster way to get your y equals mx plus b. That's 18 ninths and 2 ninths, that's 20 ninths. No, I didn't even do it in my notes. I was like, oh yeah, then it's easy after that. That mistake in the old video is on my mind. I don't want to make a different mistake here. Any questions? No, tell me in general what your questions are. I got to do that 3 more times, do I? Some of them aren't quite as long. Oh yeah. The next 2 are really good for people who have missed the lesson. Missed the first part of the lesson. The next 2 are really helpful for you, I think. But any questions on this one before I move on? Yeah, sure. Do I got to scroll up or anything? You're good? When is that awards assembly? Wednesday? Okay. So my suit will get used in November yet. Always does. 2 times in November. This year I'm going to try and put it in plastic. I know that's what you're supposed to do when you're a high-class person. So I don't have to dust it off every November. Georgia, are we good? All right. Question. Yes. The dy dx. Let me just flip over and do a little side thing for those of you. And again, if it's not perfect, if you just go, oh, I sort of get what you're saying, that'll be enough for now. Way back when, simple question like this that we did in a lot of the homework, 5x to the fourth. That's basically the first day of derivatives we did that. We thought of it and I said, oh, take the derivative. And you didn't think about it. You didn't put any thought into it. You just wrote dy dx here. And that was fine. But there's a lot going on there. There's more going on there than what you think. So let me rewind and just explain that in a different way. It's just going, to find the derivative of this, what I'm going to go is d by dx of this side equals d by dx of this side. That's what's really going on, is you're taking the derivative of both sides. So the derivative is an operator. Just like addition, subtraction, multiplying, dividing, you're doing the same thing to both sides. And this side, when you get there and you take the derivative with respect to x of 5x to the fourth, you get 20x cubed, just like before. But if you want to take derivative with respect to x of y, I don't know what that is. That's what I'm trying to find out in the question. So when I see y, I just write dy by dx. Huh? It's a different way of looking at it, but it helps in the questions we're doing. When you encounter x, just do derivative like you always did. When you encounter y, just write dy dx. That's the unknown thing anyway, so don't get upset that it's dy dx, because that's what we're trying to find anyways. So in that last example, when we ran into all these dy dx, instead of being annoyed that they're there, we should be happy they exist, because that's what we have to solve for. That's the unknown in the question. Yeah? A little better? Yeah, as long as it's a little better, it's going to be okay. I'm telling you, once people practice this stuff, they don't think it's the hardest thing ever. And we're going to use it again in the next lesson on Monday. It says find y prime if x squared plus root y equals x squared y cubed. Sorry. So what they want is dy by dx. So I'm going to do d by dx of both sides. I'm doing d by dx of x squared plus y to the 1/2 equals d by dx x squared y cubed plus 3. I did one thing there without even thinking about it. I literally did not think about it. When I saw the root y, I wrote y to the 1/2. Yeah, so I hope that didn't mess you up. I hope we've done enough like that you're good. Julia, question? 5, thank you. I was so busy getting ready to explain that y to the 1/2, I wrote 3 instead of 5. I would have got away with it too. Can you see why I would have got away with it? Can anyone see what's going to happen next? I could write 5, 3, 27, 402, and it won't actually end up mattering. But all right, I got to do d by dx of each one of these terms. There's 1, 2, 3, 4 terms to deal with. What's the easiest term to find the derivative with respect to x? 5, because that derivative is 0. I'm going to write it way over here because I don't know how much space I'm going to need for this, but I'm just trying to do them work my way up to help both groups of people that we have in the class today. What's the next of these 3 terms to find the derivative with respect to x? X squared. We don't have to do anything special there. The derivative of x squared is still 2x. Even with all the crazy stuff we're doing today, that's not so bad. I say this one's the next easiest, so I'm going to go after that one. So I'm going to try and do this one, explaining it right from the beginning, and then hopefully that's enough to help you with this semi-crazy one that's over here. Derivative of y to the 1/2. If you're having trouble with these, imagine a little bracket around the y, because the y is special in this situation, because I'm finding derivative with respect to x, and when I see the y, I know I've got a little bit of a problem. The first step is to do the first step of chain rule, which is the derivative of the outer function evaluated at the inner. I've said it in the fancy way. You might say it like, just find the derivative of y like you always would have before this d by dx thing came along. The derivative of y to the 1/2 is 1/2 y to the negative 1/2. That is totally fine. But chain rule says, then take the derivative of the inside. And what's the derivative of y with respect to x? I love that line in this moment in the lesson, because it might be the moment where it finally goes clunk. Oh, I get it now. What's the derivative of y with respect to x? dy by dx. That's literally what that says, is that's the derivative of y with respect to x. I don't know what it is. That's the unknown in the question. So when it appears, instead of being like, oh, it's the stupid dy dx, you should be more like, that's what I need to solve for. When this question's over, my last line has to stay dy by dx equals. So it better appear somewhere along the way in the question if I'm going to have any chance of solving it. My wires are driving me crazy here. Okay. Now I got this thing. What is it? It's a product rule. So I'm going to let Georgia, if she wants, do the first step of product rule. And then I'm hoping that there's somebody that arrived in the second half. Georgia wants the second half. Only if you really explain it. She did a great job of explaining it last time. She used the right words and everything. She might have done better than me. So listen carefully to her words. I'll only get involved if she makes a mistake. Yeah, okay. Go.
First, you want to take the product rule, so remove first time and second plus derivative of the second times.
I'm repeating her words only for the video. She said it's a product rule, so derivative of the first times the second plus derivative of the second times the first. Go ahead. What's derivative of the first?
Derivative of the first is just x, so 2x,
Yes?
and then times the second is y.
That's the derivative of the first times the second. Derivative of x squared is 2x times the second. No implicit differentiation has happened so far. That part we could have done before we showed up today.
Then we're adding
The
the
derivative of the second. So we get derivative of y cubed. Trouble.
So if we take the outside, since it's changing once again, you go 3y.
Mm-hmm.
And then the derivative of the inside is 2y over dx.
She says the derivative of y cubed is 3y.
And then we have to do the inside, which is 2y over dx.
3y squared.
Why is this different? 3y squared. Oh, sorry, cube. Sorry. I'm squared.
3y squared, yeah. Okay, good.
And then you do the derivative of the inside as dy over dx.
The derivative of the inside is dy dx. So if you're having trouble with these, every time you see a y, just think of a little bracket around it. And you got to go 3y squared times the derivative of the inside, which is dy dx. And don't be upset it's there. You should be happy it's there. That's what I'm trying to solve for in this question. So dy by dx better appear in there. Oh, I would have forgot if you didn't say that. Oh my goodness. Times the first. Yeah, and for me, lots of times when you're doing product rule, you have to repeat it twice. You go, okay, derivative of the first times the second plus derivative of the second, and then you're like, oh, hang on, what was I doing? Derivative of the second times the first, and it's easy to get distracted and forget that piece. The rest isn't too bad. No, it is. It's awful. It's the algebra that stopped many of your former classmates from being here because they couldn't get the algebra to work. But hopefully for you, the algebra, you're like, once you get to the algebra, you're like, okay, now I can just isolate dy dx. It'll be all right. Okay, so let me bring the terms that have dy dx over here. Minus 3x squared y squared dy by dx equals 2xy cubed. Oh, I don't like how I wrote that. That was awful. 2xy cubed minus 2x. Oh, I better check that. I lost focus there. I could feel it. 1 over 2 root y dy dx. That's that term. Bring this one over, which is 3x squared y squared dy dx. Bring that over. 2xy cubed stays and minus 2x stays. And then Ethan helped us out here with what to do with this mess. Because when you first see the messes like this, you're like, what do I do now? What do you do now? Anyone but Ethan. Or Georgia. Yeah, it's a really awkward situation with a really easy solution to the problem. Just common factor dy dx. And then divide by that big mess that you've made. And keep focused so you don't make a mistake. Two potential things you're concerned about. Didn't even do that one either. Two potential things you're concerned about. The first one is this fraction in the denominator. That was actually my second one. Yeah, it's a problem. It's not going to get better. It's only going to get worse. That thing is buried in there tough. It will be tough to get that thing out of there. If I multiply top and bottom by 2 root y, now I'll have all this stuff multiplied by 2 root y, and then this will be multiplied by 2 root y, and things won't be a whole lot better. Then I'd have to multiply by the conjugate of this and this, and it gets messy. You can try it out, but my wisdom tells me there's no way out of this. I don't think I can make it better. Ethan disagrees. Ethan, tell me.
What do you mean you have to multiply the numerator by 2 root y? Can you just, think of it as trying to make an equivalent fraction?
If I want, my move to get rid of 2 root y is now to multiply top and bottom by 2 root y. That will get rid of that denominator. So things will, at first glance, be better. But look at the mess that happens. 2xy cubed minus 2x all times 2 root y, which if I distributed, oh boy, things are going to get even more wild. Things did get a little better down here. That's now just 1. And then this term is negative 3x squared y squared times 2 root y. And it would be hard to argue that was necessarily better. You might like it better. Then if I wanted to get rid of this root in the denominator, I'd have to multiply the top and bottom by 1 plus 3x squared y squared times 2 root y. Distribute all that and have another big mess there. I don't know if it's going to get better. Okay? So this is where the wisdom in these comes from, is that sometimes this move will help. And you can try them and see if it gets better. And we had them all rigged up before you got to this level so that it would work out nuts. We wanted you to learn the tricks because you needed them. But you might find moving forward that when you get here, you'll be unhappy, but maybe that's the best we can do, even though it's a little bit messy. The other thing I want to say about this is, here's a dy dx with x's and y's in there, and that may bother you, but it's going to be okay. Because if they wanted me to find dy dx, they'd give me at least x, which I could sub in, and then I could go back to the original equation and sub in that x and get the y. The truth of the matter is, in this chapter, most times they give you the x and the y. They'd say at 1, 2, or something like that. They'd give you the x and y you needed. Okay, so we won't leave you stranded without the information you need. And I know dy dx now has x's and y's in it, but that's not going to be a showstopper. Okay? Show that dy dx is defined at every point. What? I don't even know what they're asking. But I do know I need dy dx, so here I go. D by dx of both sides. The left side wasn't too bad. Derivative by dx of 2y is 2 dy dx. First term on the right side wasn't too bad. Derivative x squared is 2x. Then this crazy one, sine y. Derivative of sine y is cos y. Then times the derivative inside is dy dx. I'll let you digest that for a second. I'm all open for questions. I just want to show the next steps of how then I would get dy dx. Bring this over. And common factor that dy dx. And then I'm going to answer the question and pause for questions. Wow, did I ever write that? Odd. Let me just fix that up there. 2 minus cos y. It says it's defined at every point. Well, the only way this could be undefined is if 2 minus cos y was equal to 0. And at first glance, you might be like, okay, well, yeah, if this has solutions, the denominator is going to equal 0. This thing's going to be undefined. So let me just try and solve it. Negative cos y equals negative 2. Cos y equals 2. I need cos y to be equal to 2. And I'll get some calculator help in a second, but I hope there's somebody that can go, this is not going to happen. Is there somebody who can explain why cos y cannot possibly equal 2, Ian? Cos y goes between negative 1 and 1. This has no solutions. Therefore, dy dx is defined everywhere. There isn't going to be a domain issue on dy dx because the denominator never equals 0. I went reasonably fast there. So if there's a step you have a question on, let me know. Georgia, what do you got? Derivative of sine y is cos y times the derivative of the inside. So now your bracket is here instead. Times the derivative of the inside, which is just dy dx. Again, when those dy dx's pop up, level 1 of understanding this is like, oh, if I see y, I just write dy dx. Yes, absolutely true. Level 2 is, oh, and I'm sure glad it showed up, because that's what I'm trying to solve for. So when the dy dx's show up, you go, oh, that's what I'm after. Good. That's the unknown. So then when people are first doing these, they're like, well, dy dx, what good is that? What am I going to do? You got to switch your perspective and go, those need to appear in this method for me to be able to solve for dy dx. Other questions there? One more crazy practice one. This is the one. d2y by dx squared. The second derivative. Well, I'll get to that in a second. Let's just do the first derivative, and then we'll talk about the second derivative. So I want to do d by dx of both sides. 2x cubed minus 3y squared equals 8. I'll do the easy ones first. Derivative of 2x cubed is 6x squared. And over here, equal to 0. Is there someone who missed the first part of the lesson who feels brave enough to handle negative 3y squared when taking derivative with respect to x? Yeah, do it. Minus 6y. So the first part of the derivative is just the same as we've always done. Then what? dy dx. And when it appears, don't be upset, because that's what we wanted in the first place, was dy dx. Now, I know enough about differential equations, fancy word, to know that I could now just go d by dx again. You actually could. You don't have to isolate dy dx to go d by dx again. But the algebra that comes out of it is a little bit tricky, so maybe what you'll want to do is isolate first. Did that sound like I was showing off? I really didn't mean it to be like that. I meant it to be like, if you want to go ahead and take derivative with respect to x of this thing, you can. But it might be easier when you're first doing them to do a little isolation first and see if you get a little simplification. And here you really do. You get dy by dx equals, the negative 6 cancels. I get x squared over y. How nice is that? That's a little tidier. And here we get another chance at all of this thinking. Now, second derivative. It was dy by dx, and I'm going to write something that might bother you, and you should definitely spend your next 3 days off thinking about it. I'm going to go d by dx of dy by dx equals d by dx of x squared y, and I'll do the first part. This means d2y by dx squared. That means take the derivative a second time with respect to x. So you're taking the derivative of y 2 times, and both times the independent variable was x. Leading to an interesting question. Can you take derivatives with respect to different things at different levels? And the answer is yes. Coming soon to a calculus class near you, we could do d2y by dx dy. That is, you take the derivative the first time with respect to x, then the second time with respect to y. We'll leave that on the shelf for now. That's a long way away. Ethan, you had a question there?
I know that there's something to do with it being like an operator and not really like an equation, but why would it not be
Yeah, yeah. It feels like maybe you should multiply it there. Is that what you mean? Yeah. It's because it's an operator. D by dx is an operator. And when you do the derivative of the derivative, you get the second derivative. If this was dy dx times dy dx, so this is actually d by dx of dy dx. So it's reminiscent of this. This isn't f times x, it's f of x. So the way I've written it this time is d by dx of that thing, not d by dx times that thing. Yeah, subtle little point he's grabbed onto there. So let's try this crazy derivative. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Maybe not that bad. A little quotient rule with dy dx, and there I'll do it slowly. Derivative of the top is 2x times y minus derivative of the bottom, which is dy dx, times the top, which is x squared, and then y squared. That is nice. You should be happy if you get that answer. Like really happy with yourself. You're like, oh, I'm so good at calculus. It's going to be a great year next year. Yeah? But just to get warmed up for some stuff that's coming up here, we can do a little better. Oh, did you hear the noise Ethan involuntarily made there? He went, oh. So I'm going to give you time. I have moments here before the spell goes. I can give you time to try and see what he saw. I wrote 2xy minus blank x squared over y squared. Can you find the blank? I know I've been on about it before. Some of you hopefully are going to be teachers and professors someday. Do not be uncomfortable with the uncomfortable pause. It's uncomfortable to me standing up here waiting for something to happen. But for most of you, it shouldn't be uncomfortable. Most of you are like looking around going, what is it? What's going on? Why? What's the aha moment here? Ethan, where is it?
We already know what dy dx is.
Flashing red lights. Do, 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 do. We don't need to leave dy dx in this thing. We don't have to make an equation that'll have multiple subs going this way and that way, like my order from Subway from my family. What a mess that is, trying to get everyone's sub just right while as I order online. You don't have to do multiple crazy subs here, because this is x squared over y. Oh, it's good stuff. Do the x squareds cancel? Yeah, probably we want this. Multiply top and bottom by y. That's a good move. Because then what I get is d2y by dx squared. Multiplying everything by y, this one's 2xy squared. Multiply everything by y, this one's minus x cubed. And this is y cubed. Look at that. Oh, that's beautiful, powerful, beautiful, powerful mathematics. Oh, x to the fourth, yes? Oh, I'm sure glad I caught that. Was someone going to catch it anyways? I hope so. I hope someone's out there going, you tripped on the 1 yard line there, Mr. Todd. You're about to score a touchdown, and then you dropped the ball right there. Okay, x squared, x to the fourth. This is great stuff, folks. I'm telling you, it's great stuff. It's the type of math that causes you to make random noises in the middle of the questions where you're like, oh, yeah? 3 beautiful days to knock this down in the middle of a chapter. It's beautiful timing. We're not even into the great stuff of this chapter yet. Does anyone need more time on this one before Georgia rewinds us to the last one? Need more time here? You wanted this one? Sure, you can stay here because it's period 2. I'm period 2 prep 2, so you can stay here if you want. I was confused when I gave you instructions this morning. Yeah.